Hello everyone, welcome to this video. In this video, we'll be proving the assertion that if we are given some set 1, 2, 3, 4 and so on up to n minus 1, this set forms a group under multiplication modulo n, right? If and only if n is prime. So that means we have to prove both the cases. In the first case, we assume that n is prime. Then we will prove that this set forms a group under multiplication modulo n, right? This thing we have to prove. So to prove this thing, we have to prove all the four group axioms. That means the closure property, the associative property, existence of identity and the existence of inverse. So let's get started. These are the elements and we have this as our operation, multiplication modulo n, where we multiply two elements together and then we divide it by n. Whatever is the remainder, that is our answer, right? For the closure property, let's take two elements a and b from G, right? This set G. So let's apply the operation multiplication modulo n to it. So it would be a, b. First of all, you multiply them and then you take its mod n. When you take its mod n, it would definitely be smaller than n, right? So by the division algorithm, you can write, because you are dividing ab by n, so you would get some quotient and you would get some remainder here. There could be something. So you can write it like this: ab is equal to nq plus r, this form. And what is this r? This is obviously greater than or equal to 0 and it is obviously less than n. This is according to the division lemma, division algorithm. Now what is the case when r is equal to 0? If r is equals to 0, then in that case we won't have this term. So that means your AB would be equal to NQ. So that means n would divide AB. However, this cannot be possible because your n is a prime number. It cannot divide any number except itself and 1, right? So therefore, we cannot have this case r is equals to 0. So that means r is not equal to 0 and hence our r would lie exactly between 0 and n. So that means it would be some member from this set only, 1, 2, 3, 4 up to n minus 1, correct? So therefore we would say this is some equal to r. Why? Because AB, you can write AB as what? You can write it like this: nq plus r. And when you take it mod n, under mod n, because this completely divides with n, this term would be cancelled and you will be just left with the remainder r. So this is r and this is some member of G. Hence we say our set is closed under this operation, proving the closure property. For the next, we wanted to show the associative property. We say because multiplication is associative, so multiplication modulo n is also associative. For the existence of identity property, we take some element a from G, right? Now we say 1 is the identity of this group. Why? Because if you take multiplication modulo n of 1 with any number a, right, from G, then you will get back a, and when you take a has been taken from G, so obviously a is less than n, correct? So when you take a mod n, it would just be a, correct? Why? Because a is less than n. So therefore we say, because on applying this operation we again get back the same element, hence 1, which is a member of G, is the identity element of G, and this is what we have to prove. For the next part, we wanted to prove the existence of inverse. For this, if we take some element a from G, we have to find what is a inverse here. Is it also present in G for all the elements? If yes, then it would be a group. Now let's take element a from G. So obviously it would either be 1, 2, 3, 4 up to n minus 1. So you can write it like this. It is either equal to 1 or it is greater than 1 and less than n. Now because we know n is prime, so the GCD of this number a with n has to be equal to 1 because both of them are prime. So according to the definition of GCD, we have also learned a theorem about it, which states that we would have two integers, let's call them by u and v, right, such that this first member multiplied with the first integer plus the second member multiplied with the second integer is equal to 1, because their GCD is equal to 1. So that means we have this expression. So This is one thing. Another thing, we can apply the division algorithm onto n and u. So that means we are saying for whenever this n divides u, right? Whenever we are dividing u with n, so we would have some quotient here and some remainder here, so that we can write it like this: u is equals to nq plus r, right? So u is equals to nq plus r, where again the remainder lies between 0 to n, and it could also be equal to 0. What if it is equal to 0? If it is equal to 0, then we would not have this term. So again we would have u is equals to nq. So you can substitute the value of u is equal to n2 here into this expression here in place of u, so that you would have a nq plus nv is equals to 1. So you can take n common from these two terms, so it would be this. So basically your n is a prime number, right? It is greater than 1, and moreover these are integers. They cannot be written like rational numbers, like some number here. So therefore this thing cannot happen. Why? Because either n has to be a rational number divisible by it is greater than 1, either it has to be less than 1, or this has to be a rational number. So therefore this case is discarded here. If this case is discarded, so that means your r would definitely lie between 0 and n. So definitely r would be member of G. So that means you would have instead of au plus nv is equal to 1, you can substitute the value of u here as what? nq plus r, right? So you can substitute u is equals to nq plus r here, so that you would have nq plus r. Now what you can do from this term and from this term, you can take n as common. So you will be having this term, and plus the term ar would be left as such. This is equal to 1. Now when you take mod n of it, so this term would be completely divisible by n, so it would give you the remainder as 0, and this term would not be divisible by n, so it will be as such, ar, that is equals to 1. So you can write ar, we are multiplying two terms a and r, and then you are taking mod n. So what is it? It is nothing but your multiplication modulo n of a with r. So you obtained this as equal to 1, which is what? The identity of the group. So that means for any arbitrary member a from G, you have obtained r from G such that when you apply this operation, you get the identity. Hence r is the inverse of a. So each element would have an inverse in G. So therefore, because we have all the four properties satisfied here in this case, hence we would say this forms a group under the operation of multiplication modulo n, right? This proves one part of the proof. For the next part, we assume that if this set G is a group under multiplication modulo n, then n is a prime number. So let us suppose that if possible n is not a prime number. If it is not a prime number, then it is surely a composite number which could be written as the product of many prime numbers. So let's suppose that n is the multiplication of two numbers p and q such that they are not exactly equal to n, they are not exactly equal to 1, they lie in between 1 and n minus 1 such that the product is n. So if that is so, because n is equals to pq, so pq would be written as 0 mod n, because when you divide it by n, so basically you are dividing n by n. So when you divide n by n, you would have 0 as the remainder, because it would be completely divisible by n. Hence pq is equals to 0. But this element 0 is not a member of A, because all the members of G, they start from where? 1, 2, 3 up to n minus 1, and 0 is not present here. Hence we have a contradiction, because this pq is not present in our group, right? So therefore our supposition was incorrect, that n is not a prime number, so it has to be a prime number, and this is what we wanted to prove here in this particular case. So I hope you understood this proof well. That is it for this video. Thank you for watching.